Okay, so wait, there's a comment already. Let's see. But didn't the email say we're going back? Yeah, the email, I think it says we're going back on the 15th, I think. That's because the lockdown is extended to the 15th. So technically we are going back in a week, but I just don't believe that. Last time they said we're going back on the 25th of January. That didn't happen. And then they extend that to 10th of February. That's not happening. Now they extend it again. Yeah, they're just playing cat and mouse here. I hope we go back because I do want to teach in person so I can show you cool things. Sitting at home staring at a screen, yeah, that's not fun for anybody. So yeah. Anyway, let's start the class. We're gonna learn 5 different types of chemical reactions. So chemical reactions, they come in different types. We categorize them based on how the reactants and products interact with each other. Okay, so you do need to know how to balance equations in order to do this. It's kind of like the same package. You balance the equation and you tell me which type of reaction is this. Okay, so we're going to look at 5 different types: synthesis, decomposition, single displacement, double displacement, and then combustion. Now, within combustion, there are 2 types of combustion. There's a small difference, and we're going to talk about that. All right, so let's start with the first one, synthesis reaction. The names of these reactions are pretty intuitive. Synthesis. In English, the word synthesis means to make. Photosynthesis, you make things from light. Okay, synthetic means man-made. So photosynthesis synthesis reaction is just you have a chemical reaction. You got 2 reactants, A and B, let's say. They combine and they stick together to form a bigger thing. So 2 smaller things to combine to form a more complicated structure. So the general equation is A plus B, arrow AB. By the way, A and B, I'm not referring to any specific elements here. I know B is boron, but A doesn't really have a meaning. They're just generic letters. It could be anything. So imagine 2 things. They're separate, but after the reaction, they're now one and the same. That would be synthesis. Okay, that's one of the easiest ones to understand. And here are some examples of synthesis reactions. Zinc and sulfur, they can combine to become zinc sulfide. Okay, sodium and chlorine, a very common substance is formed. Salt, sodium chloride. Salt is table salt, the thing you have in your kitchen. But sodium is very explosive. Chlorine is a deadly gas. It was used as a weapon. But this reaction from 2 very deadly substances, you can derive salt, the thing you put in food. So chemistry is actually quite fascinating. And another example is HCl, the gas version of the hydrochloric acid. Combine that with ammonia. That's bleach. No, not bleach. Sorry. Ammonia is not bleach, by the way. Sorry. Ammonia is ammonia, something that you can also buy. They will form ammonium chloride. Okay, that will be a solid. So that's another synthesis reaction. So synthesis, just to recap, 2 reactants, they come together, they link up, they have 1 product. You have 1 thing that is formed. Any questions about that so far? Okay. The next one is the opposite of synthesis. Okay, you would have decomposition. Decomposition, just look at the name. Decompose means to break down. Okay, when things die, their bodies decompose. Decomposition, you take a big thing, let's say AB, you break it into its elements. You break it down into smaller bits. So you have more than 1 product, but you start with fewer reactants. It's kind of like a divorce. If synthesis is a marriage, then decomposition, they split up. Does that make sense? To give you a real example, this. Airbags. All vehicles are equipped with airbags, and inside you have this compound, sodium azide. Okay, when there's a collision, this reaction immediately reacts and decomposes the sodium azide into sodium metal and nitrogen gas. And this gives off a lot of energy in the form of heat, and this will expand the nitrogen gas. So this gas expands with high temperature, quickly filling the bag so that your face wouldn't hit the windshield or the steering wheel or something dangerous. Instead, you hit the bag. Okay, and well, not if you're an infant. This is actually deadly to infants, which is why babies can't be in the front of a car. But yeah, if you have a collision, this will pop and a decomposition reaction occurs and it attempts to save your life. Okay, so that is an example of decomposition. Notice that sodium azide is a single compound, NaN3. I know that seems really weird, that violates every rule that we've learned about chemicals. This is one of those special ones. The world of chemistry is big. We're only starting out, so we're learning the basic rules. Of course, many things break those rules. We're not going to concern ourselves with that. The name of this is weird as well. Azide, what? That's a common name. That's not the proper IUPAC name. So if you have any of those questions, well, don't worry about it. So sodium azide breaks apart to form two different products in energy. So decomposition. You need to be able to recognize decomposition and synthesis. Okay, so let's move on to the third one. Single displacement. Single means one. Displacement means to move. If something is displaced, well, you just got bumped. You got replaced by something else. Okay, single displacement, you have one replacement. Some people call this the single replacement reaction. I guess that's okay, but the proper way is some single displacement. What you have is, let's say, A plus BC. Okay, BC, they're a couple. B is bonded with C. And then A comes along, just like, a drama flick, especially those Korean dramas. Something happens in a love triangle, and somebody gets displaced. B gets dumped, and then A hooks up with C, and B goes and they cry in a bar or something along that line. So that's single displacement. You make one replacement. I replace one compound with another, so that A was alone before. Now A has a partner. B had a partner, but B got dumped. So now B is alone. So that's single displacement. And this is an example of that. This is a very expensive demonstration. Okay, even if we go back to school, I have all of these things, but that costs like around $50 to demonstrate that, because of how expensive silver nitrate is. So silver nitrate react with copper to form copper 2 nitrate and silver metal. So here is single displacement. Copper was single, just solid copper. Silver nitrate had a partner, silver nitrate. That's an ionic compound dissolved in solution. That is a colorless solution. Copper is of orange metal. You can dip this copper into the silver nitrate, and you just wait a couple of hours and you come back. You're going to see picture B. The solution will turn blue, and you will see a silvery fuzz start to collect over your copper wire, and that silvery fuzz is pure silver. So you can extract silver from silver nitrate using this method. And the blue comes from the copper 2 nitrate. Now that's the ionic solution, and that has a blue color. Okay, so the blue comes from the copper 2 nitrate solution. The solid silver form around the copper wire. This is single displacement. You switch the two metals, one for the other. Okay, any questions? Wait, this only happens if A is a stronger chemical than B. Yes. We're not concerning ourselves with the hierarchy of the reactivity series. Okay, in grade 11 chemistry, we're going to learn this again. But in grade 11, you do have to know some metals can display other metals, but not some other metals. Okay, that came out a little weird, but you see what I mean? It's just like if you have, let's say, a romantic partner, you might get dumped. But they're probably not going to dump you for someone that they think is worse than you. You see what I mean? Let's say you have, if you're a girl, you have a boyfriend, or yes, let's just go with that. You are probably not going to dump your boyfriend for some random person on the street if you have a boyfriend. But if you're, I don't know, Niall Horan or Drake, or I don't know who's popular nowadays. I don't know, Maroon 5. Who?
Justin Bieber.
Justin Bieber. Okay, it pains me to say that. Let's go with Justin Bieber. So if Justin Bieber shows up, yeah, I know you're dumping your boyfriend right now to go with Justin Bieber. See, there is a hierarchy, but you're probably not going to be able to steal Justin Bieber's wife from him because, you know, the hierarchy. Does that make sense?
Michael B. Jordan.
Who?
Michael B. Jordan.
Michael B. Jordan. Yeah, he's pretty good looking. Yeah, see, you would probably dump your boyfriend for Michael B. Jordan, but some random dude on the street, nah, probably not. You see, yeah, metals work like that as well. There is a hierarchy. Some metals are more attractive, literally, than other metals, and they will switch. Okay, but we don't have to concern ourselves with which metal is more attractive to the negative ion. Don't worry about that. The equations that I'm going to give you is always the more attractive metal will swoop in, break up the couple, and, you know, do a single displacement. So copper is more attractive than silver. So therefore, this will happen. Does that make sense? So yeah, that's a very good question. Thank you. Okay, the fourth reaction is, well, you guessed, double displacement. You have single displacement. You have a love triangle. Well, this is even more messed up. Okay, you do a switch. You had a couple. You have another couple. You know what? They both get into arguments, and you know, I hate you. So they go out and they find a new partner. It happens to be each other's partner. That's what happened. You do a double switch. The two compound switch their metals with each other. Okay, so AB plus CD. Well, after the reaction, you have AC plus BD. Like you go to the prom with somebody, you don't go back with that same person. Sad, but it happens. So here is an example of a double displacement reaction. Usually this occurs in solutions. Two solutions mixed together, their ions start to dance in the beaker, and they find a new partner. So silver nitrate, again, very expensive, plus salt water, that's sodium chloride. When you mix them together, you're going to get a white powdery substance form in your beaker. Those two solutions, before they mix, they look just like water. You wouldn't know that. You don't know what it is until you do some experiment to find out, because they both look like water. You mix them together, sodium nitrate, NaNO3, that still looks like water, but that silver chloride is a solid. It does not dissolve very well, so it comes out of solution as a solid. So that is what we call a precipitate. Okay, a precipitate doesn't just refer to rain and snow. In chemistry, it refers to the solid residue that forms when you mix two aqueous solutions together. Okay, so it is not very soluble. So silver chloride is a solid. It looks milky because it's a powder in a liquid. So that will be a double displacement. You see, you switch. Silver is swapped for sodium. Does that make sense? So far, we learned 4 chemical reactions. You can tell which one is which by tracking what did the reactants do in order to react. Did you get married? Did you get a divorce? Is there a love triangle? Did someone get dumped? Or did you do a double switch? Okay, that's the question that you should be asking. The last one that we're gonna look at is combustion. Okay, combustion is very intuitive. You burn stuff. That's the idea right there. But in order to burn stuff, you need oxygen. Okay, without oxygen, nothing burns, which is why a fire blanket works. If something is on fire, throw a fire blanket on it. You cut off the oxygen supply, the fire quickly dies out. So if you're cooking something, I don't know, this is something, there's a fire in your pan, you just put the lid on it, that will run out of oxygen soon and the fire dies. So you do need oxygen in order for combustion to occur. So combustion is literally the reaction with oxygen. Okay, and the products depend on what the reactions are. So a hydrocarbon is what we're going to learn. We're going to burn hydrocarbons. A hydrocarbon, just look at the name, hydrogen and carbon. It's a compound made of carbon and hydrogen only. Those things burn really well. Natural gas, methane, is a hydrocarbon. It has carbon with 4 hydrogens. Okay, gasoline inside of a car, that is 8 carbons and 18 hydrogens surrounding it, that burns really well. Propane, that's a hydrocarbon. So all of these will burn. They're all flammable. Okay, and that is a combustion reaction. There are 2 types of combustion reactions. We're going to first talk about the complete combustion reaction. Complete combustion, as the name suggests, the reaction is finished. It goes to completion. You use up all of your fuels and you produce some very clean products, carbon dioxide, water, and energy. Okay, and this only happens if you have a bountiful supply of oxygen. So here is the general equation. Notice that this is a bit more complicated than the others. We're not just using A, B, C, D anymore. CXHY. Okay, what? Instead of numbers, I used X and Y because they can be anything. Okay, it could be C1H4. That's just natural gas. It could be C3H8. That would be propane. C8H18. That is gasoline. So hydrocarbons is what I'm trying to say. You take something that is made up of carbon and hydrogen, you light it on fire using oxygen. What do you get? You get carbon dioxide, you get water, and you release energy. You need to know this equation. You need to know the reactants. You need to know the products, carbon dioxide, water, and energy. That's always true for complete combustion. You will only get complete combustion, however, if you have excess oxygen. If you don't have enough oxygen, complete combustion won't occur. Instead, you would have incomplete combustion. All right, so if you have complete combustion, you have a blue flame that is really hot, really high temperatures. Oh, I'm sure you've seen blue flames before. If your house has those old stoves, you turn it on, blue flames come out. Okay, but now we use electric stoves. We don't have an open fire in the kitchen anymore. But if you ever see blue flames, it's because that's complete combustion. It is hotter than the orange flames that you see at a campfire. Okay, so flames are blue and hot. And the only products are CO2, H2O, and most importantly, energy. That's why we burn things. We burn for the energy. We don't burn to create carbon dioxide. That's a side product. That's an unfortunate side effect of burning. We want the energy. We want to use the energy to cook food, to warm our homes, to power our cars and whatever. And water and carbon dioxide are released from the pipes. Okay, so that's complete combustion. excess oxygen. You have blue and hot flames. You make CO2 water and energy. Okay, you need to know the equation. You need to know how to balance this equation. Okay, so let's move on to incomplete combustion. Incomplete combustion, like the name suggests, the reaction didn't quite finish all the way because you have a limited supply of oxygen. You don't have enough oxygen to burn everything cleanly. And this is way more complicated. You have your hydrocarbon, CXHY, again, X and Y can be anything. You burn that with oxygen, okay, cool, but you don't have enough oxygen to see this through. So you have a lump of carbon left, the carbon solid, we call it soot. Those are the ashes. Okay, if you see a campfire and you can see the smoke coming out, that's what you're looking at, the solid carbon dust particles that are flying in the air. You create carbon monoxide, carbon dioxide, and water. Of course, it's energy. Okay, so if you ever see a smoke from a fire, then you know this is incomplete combustion, because complete combustion, you wouldn't see the smoke. Carbon dioxide and water vapor, they're invisible. You wouldn't be able to see it. If you ever read the book Lord of the Flies, I don't know what books you read in English, probably not Lord of the Flies. But yeah, that's a pretty famous book. A bunch of kids got trapped on an island. They have a bright idea. Go to the mountaintop and light up a fire so that the planes that fly by can see our signal fire and we get rescued. It works because it's incomplete combustion. Okay. Again, if you don't have enough oxygen, this occurs. And flames are orange and cool. By cool, I don't actually mean it feels cold. Okay, this is a relative term. Compared to the blue flame, this is cool, but it still burns your hand. It's still quite hot, and it may have a black smoke because of the solid carbon. The products, there's 5 of them. Carbon dioxide, water, energy, just like complete combustion, but in addition, I highlighted in red, you have carbon monoxide and soot. Okay, is that clear? The difference between complete versus incomplete combustion. Okay, cool. One last thing before we finish. This might save your life. Carbon monoxide is one of the products of incomplete combustion. Okay, we call it the silent killer, like a ninja. Just like a ninja, you can't see it, you can't smell it, you can't taste it, and it kills you. Okay, colorless, odorless, extremely toxic. It will kill you without you knowing. Okay, you could be breathing it right now as you're listening to this lesson, and you suddenly feel dizzy, you feel weak, you feel sleepy, and you fall asleep. You never wake up again. How do you not die from carbon monoxide? Well, you have to understand how you can get carbon monoxide so you can avoid it. It kills you by competing with oxygen inside of your lungs. Remember in biology, we learned that your lungs, blood will come into your lungs, into the alveoli. Oxygen will sit on your red blood cells. The red blood cells will happily carry that oxygen to your cells, dump it off, and then it goes back to the lungs and grab more oxygen. Okay, that's how you deliver oxygen. You chauffeur the oxygen into every single one of your cells. But if you have carbon monoxide, the blood actually prefers carbon monoxide over oxygen. Okay, carbon monoxide binds to, well, it binds to your blood better than oxygen. So if oxygen binds to your blood, no problem. If you have carbon monoxide, it sits on top of your red blood cells. And then when oxygen shows up and tries to bind, it doesn't work because someone is in your spot. And the carbon monoxide won't let go. and you can't breathe carbon monoxide. So you literally die of suffocation. There's oxygen available. You're breathing it into the lung, but your blood is not picking up. You die. Okay. How do you prevent that? Well, actually, let me just finish this off. How do you prevent that? Well, you make sure that wherever you are, you don't have a lot of incomplete combustion. And that is a product of incomplete combustion. That means keep your windows open if there's an open fire. If you have a car in the garage, if you're going to turn on that car, you better open the garage because carbon monoxide will start to accumulate. All right, so soot is another product of incomplete combustion. Okay, if you see that black smoke, solid carbon. This causes pollution, and if you have incomplete combustion, then the flames are not as hot, and you don't produce as much energy. So that's quite wasteful. So if you want to know whether something is complete or incomplete, you can just look at the color of their flames. Orange means incomplete. You see black smoke or soot, incomplete. If you don't see any of those, it's probably a complete combustion. Okay, and that is basically the end of this. Okay, so do we have any questions? For real? No. Okay. Well then, it seems like we're done. We basically learned about this 5 different types of reaction. You have synthesis, you have decomposition, single displacement, double displacement, and then you have the 2 types of combustion. You need to be able to recognize them. You need to be able to balance their chemical equations. All right, so I'm going to stop the recording.